Welcome back to linear algebra. In this video, I want to talk about the range and the kernel of a linear transformation. Before I can get to that, I suppose I should quickly review that a linear transformation is any rule which maps each vector in a vector space V, which we call the domain, to exactly one vector in another vector space W, which we call the codomain. A linear transformation is a function. We've talked about how that works in a couple of previous videos. For now, the thing that I want to really think about is the domain and the codomain. I talked about this relationship before, but I think it's worth repeating because it's a little bit odd and it takes some getting used to. We want to call the codomain into question. We don't really care if every vector in the codomain is touched by the linear transformation. That is to say, there can and very likely are one or more vectors in vector space W which do not appear as the result of evaluating this linear transformation, no matter what vector you start with. But being able to talk broadly about the type of vector that we end up with is very useful. Talking about a transformation that maps to the three-dimensional Euclidean vectors, or a transformation that maps to the fourth degree polynomials, are two very different kinds of transformations. And if my three-dimensional Euclidean vectors only ever have a non-zero z component, well, that's a very small fraction of all of the three-dimensional vectors. If my fourth degree polynomials never have a non-zero coefficient on the fourth degree term, well, they're technically third degree polynomials that way, but it's still something that we can talk about, and there might be a reason that having it defined in such a way is useful. And so we started to specify a little bit more cleanly the image of a set is the set of all vectors that come out of performing this linear transformation on that set. Things to stress here: I do not require that set S is itself a vector space. It is a set containing some vectors. It may not be closed, it may not have any of the other nice properties, but it is a set of vectors, and that's good enough. And then the range of T is the image of the domain. That gets us to the language that you're accustomed to thinking about when you are talking about real valued functions. The domain is the input values. The range is the set of all values that can come out of the function. The reason that we care about codomain, the reason that we have to introduce this extra bit in the middle, is because unlike courses that you've taken previously, where every function took on a real valued input and gave out a real valued output, the domain and the codomain were both the real numbers, we have a lot more flexibility here in the definition of a linear transformation, and so we want to have more language to talk about it. Here's a linear transformation we've talked about previously. It is the derivative on third degree polynomials, d of a naught plus a1x plus a2x squared plus a3x cubed becomes a1 plus 2a2x plus 3a3x squared. We've shown previously that this is a linear transformation. And so we might be interested in finding the range of this transformation. And it's a little bit disappointing, to be perfectly honest, playing around with this transformation and finding the range because there's not a lot to do. We know that if we take an arbitrary element of the domain R3, we're going to get an element that looks like this. So the range d of R3 is the set of all vectors, all second degree polynomials, that look like a1 plus 2a2x plus 3a3x squared for a1, a2, and a3 in the real numbers. One of the interesting tricks that we've used in the past is recognizing that if you have an arbitrary real number like a2 or a3, and then you multiply it by a constant, that doesn't change the fact that you have an arbitrary real number. And so I can perform a change of variables here. If I write just b1 as a1, not to change anything at all, if I write b2 is 2 times a2, again, no matter what I want b2 to be equal to, I can find a real number a2 that will make that work. And likewise, I'm going to let b3 be 3 times a3. And no matter what value I want for b3, I can take a third of it, I can call that my a3, and this will still work. And the reason that I care about that is because any polynomial that I can write in this form, b1 plus b2x plus b3x squared, well, I could do another change of variables if I really want to. If I let a naught, now that I've gotten rid of a, I can reuse a. If I let a naught be equal to b1, then this is a naught. If I let a1 be equal to b2, then this is a1x. And if I let a2 be equal to b3, this is a2x squared. And I probably didn't have to make that last step to notice at this point that I'm looking at the set of all second degree polynomials. So the codomain in this case is the range, or the range is the entire codomain, which can and will happen, but doesn't always happen. For comparison's sake, another linear transformation that we've talked about previously. Helps if I can write. I mapping from R2 to R3 such that I of A naught plus A1x plus A2x squared is A naught x plus 1/2 A1x squared plus 1/3 A2x cubed. This is the integration operation on second degree polynomials. You put in a second degree polynomial, you integrate, you get out a third degree polynomial. And I had you show in the homework that I is also a linear transformation. The interesting thing here now, though, is what is the range of I? Well, again, we've established I using an arbitrary element of R2. So the range of I must be the set of all things that look like this. Right? So the range of I, which we write as I of, oh, why did I do that? These are polynomials, not real vectors. This is P2 and P3, not R2 and R3. Sorry about that. I of P2 is the set of all vectors, all third degree polynomials, A naught x plus 1/2 A1x squared plus 1/3 A2x cubed, such that A naught, A1, and A2 are real numbers. Unlike what I did with the second degree polynomials, or with the differentiation operation, with these, I'm missing something. Right? This is an arbitrary third degree polynomial, except that it does not have a constant term. And so talking about it in terms of the third degree polynomials isn't quite going to make sense. But what I am going to notice is going to still follow similar logic. A naught clearly is an arbitrary constant. A1 is an arbitrary constant, and because of that, 1/2 of A1 is an arbitrary constant. And A2 is an arbitrary constant, and so 1/3 of A2 is still an arbitrary constant. If I want to have the number 5 here, then I pick as A2 3 times 5, which is 15. Plug in A2 equals 15, 1/3 of 15 is 5. It gets me right to where I want it to be. I can do that with any number. The range here is the set of all linear combinations of x, x squared, and x cubed. Right? That's the very definition of a linear combination. I could go through the mechanisms of trying to rewrite that using clearer coefficients if I wanted to, but I don't really care. You've seen how that works. We don't really go through all of that every time because it's something that happens so frequently. Because A naught, A1, and A2 are arbitrary constants, multiplying them by any fixed constant isn't going to change the fact that it's an arbitrary constant. And so this set is the span of the three vectors x, x squared, and x cubed. I like talking about it in these terms because it really drives home that this is not the entire codomain. We've looked at the vector space of polynomials often enough that you know that x, x squared, and x cubed are linearly independent vectors. But there's only three of them. So the dimension of the range is 3. But the range is a subset of the codomain P3, and the dimension of P3 is 4. And so that's a really nice way of being able to quickly verify that there are things missing. There are things in the codomain that do not show up in the range because the dimensions are different. Although even saying that, I've implicitly made an assumption that I haven't made clear yet. To talk about the span of the range, we have to know that the range is a vector space. Right? The span of a set of vectors is always a vector space. So we're good on this particular case. But that actually is something that we can say in general. For any linear transformation, the range of the transformation, T of V, well, we already know the image of any set is a subset of the codomain. That comes naturally out of the definition. The important idea here, I claim it is a subspace. It is a vector space in and of itself. So remember our theorem. A subspace is a vector space which is non-empty and preserves linear combinations. So that's the outline of this proof. We need to show that T of V is non-empty. Well, thinking about the axioms of a vector space, for any vector space, the zero vector must be an element of that vector space. It's the only vector that we are guaranteed to have in any given vector space, and every given vector space must have a zero vector. And because linear transformations preserve linear combinations, it must be the case that the transformation acting on the zero vector produces the zero vector. Otherwise, when you try to take a linear combination, you can just add on to it and really weird things will happen and you'll get things like 1 is equal to 2, which is a very bad thing to have happen. It's a little bit messy here because I'm using the zero vector in two different contexts. This zero vector is an element of vector space V. This zero vector is also an element of vector space V. But now that I've taken the transformation, this zero vector is an element of vector space W. And it is this zero vector that we're talking about here, which must be an element of the range. All right, so zero in the domain, zero in the domain, zero in the codomain, zero in the codomain is also in the range. Again, saying this about the zero vector is not technically necessary as long as we have any vector so that the set we're caring about is non-empty, but the zero vector is almost always the easiest one to use, so we just use it. Why not? Next thing up, we want to preserve linear combinations. That's not the pen I wanted. That's the pen I wanted. To preserve linear combinations, we need to take a couple of vectors in the set. We know there's at least one. This might be the same vector twice, but that's okay. And then let's let C1 and C2 both be real numbers. When we say preserve linear combinations, we want to show that C1W1 plus C2W2 is also in the range. All right, so again, this is want to show. We're not claiming it's true yet, but we're reminding ourselves of where we're trying to get to with this. Trying to make sure we know where we're going as we go is very important in proof, as you've seen at this point in the course, but it's always something that's worth writing down and having a roadmap. Right. We don't know a lot, but we do know that W1 and W2 are elements of the range. Well, the definition of the range is vectors that come out of the linear transformation. So there must be a V1 and a V2 in the domain so that W1 is T of V1 and W2 is T of V2, right? That's the definition of the range. The range is the set of vectors that come out of performing linear transformations. So there must have been something we took a linear transformation of to get each of W1 and W2. So now by substitution, C1 W1 plus C2 W2 is equal to C1 times T of V1 plus C2 times T of V2. And since T is a linear transformation, that means that we can bring multiplication inside. And we can bring vector addition inside. That's backwards of how we've normally used those properties in the past, but it is still those properties, and that's what matters. Now, I'm going to write this as since V is a vector space, C1 V1 plus C2V2 is an element of V. And what I really mean by that, the shorthand that I'm using there, this is a linear combination of vectors in V. And any vector space is closed under linear combinations. So since we have vectors in V and we're taking a linear combination of them, the result must still be in V. We haven't escaped our vector space by doing this. And then so by the definition of the range, if we are taking our linear transformation on an element in V, it is a member of the set of the linear transformations of every element in V. That's what the image means. The range of a vector space, or the range of a linear transformation, is always a vector space, no matter what linear transformation you're talking about. As long as it is a linear transformation, the range is always a vector space. Sometimes it's a silly vector space, sometimes it's a very interesting vector space, but vector space nonetheless. Shifting gears a little bit, the kernel of a linear transformation we're going to note as KER of T, kernel of T. It's the set of all vectors in V such that T of V is equal to 0. And that should be the 0 vector. Right? Again, you always have to take time and make sure you understand where vectors are. Vector V is in vector space V. That makes sense. We're evaluating it. We're naming it exactly what it is. And then when we take this transformation, we move to vector space W. So the 0 here is the 0 from vector space W. Making sure you know which 0 you're talking about where is important. Making sure you know which vector space you're talking about for every vector is always important. But every other vector we're going to be very clear about. Little v comes from big V, little w comes from big W. 0, well, there's a 0 in each of them. So you have to make sure you know which 0 you're talking about. Right. As an example, I'm going to go to the integral operator we were talking about previously. Remember, the integral is going to take some a naught plus a1x plus a2x squared, and it's going to map it to a naught x plus 1/2 a1x squared plus 1/3 a2x cubed. And if we're looking for the kernel of I, we're looking for an arbitrary element in I, like we have right here, and we want to know when that is equal to 0. So a naught x plus 1/2 a1x squared plus 1/3 a2x cubed is equal to, well, the 0 polynomial is just equal to 0. This is a fairly easy one to establish. This is actually kind of a boring kernel to look at, but I think that sometimes makes it a nice first example. There's not a lot happening here. We are saying that two polynomials are equal to each other. And the only way two polynomials can be equal is if each pair of corresponding coefficients is equal to 0. So we get that a naught must be equal to 0, and a1 must be equal to 0, and a2 must be equal to 0, which means that the only vector that we can get out of this is the 0 vector. Right? That always happens. You always have that the 0 vector is inside the kernel, but sometimes it's interesting to know when there is something else going into the kernel. I'm going to have you look at an example a little bit later on where you find a kernel that is not going to be just the 0 vector. But before I get to that, I want to prove one last theorem. For any linear transformation, the kernel of T is a subspace of the domain. As with the range, showing that the kernel of T is a subset of V is incredibly easy. The definition says that every element in the kernel of T must come from set V. So we know that it's a subset. We want to show that it is a subspace. And as with the last proof, to show that something is a subspace, we need to show that it's first non-empty. And we'll do that the same way we did with the range. No matter what transformation you're looking at, a linear transformation acting on the 0 vector of the domain will always return the 0 vector of the codomain. And so, again, paying attention to where your vectors are coming from. The kernel is a subset of the domain. So it is the 0 vector in the domain that is an element of the kernel of T. Sometimes that's really obvious, sometimes it's a lot less obvious, but it is always something we have to pay attention to. Now, we want to show that the kernel of T is closed under linear combinations. So let's take two arbitrary vectors in the kernel. Since the kernel is vectors in the domain, I'll call these v1 and v2. And we need a couple of constants, c1 and c2. And we want to show that c1 v1 plus c2 v2 is in the kernel of T. Turns out that's actually fairly easy to do. By the definition of the kernel, it must be the case that T of v1 is equal to the 0 vector in W, and T of v2 is equal to the 0 vector in W. So C1 v1 plus C2 v2 by substitution, I'm sorry, I forgot something in that. C of T, So the transformation T acting on this linear combination, C1V1 plus C2V2, we can use the fact that T is linear to split it up. This is the way we're used to dealing with that. C1 times T of V1 plus C2 times T of V2. Right? T is a linear transformation, which means we're allowed to do that. And T of V1 is 0. T of V2 is 0. 0 times a constant is 0. 0 plus 0 is 0. If the transformation acting on our linear combination gives us the 0 vector out, by definition, C1v1 plus C2v2 must be in the kernel of that transformation. All right. So we know that the kernel is always going to be a vector space, which might make it a little bit easier to figure out how to name this thing. So let's take a look at this transformation. It's an interesting one. T maps from the second-degree polynomials to the three-dimensional Euclidean vectors. T of a naught plus a1x plus a2x squared is going to be the vector with components a naught, 0, and 0. This is not a linear transformation we've dealt with before, so the first thing we're going to have to do is verify that it is in fact a linear transformation. And then the interesting thing that I want to look at is finding the kernel of this transformation. If you're curious, I encourage you to look for the range of this transformation as well. Honestly, the range of this transformation is very easy to find. The kernel is where things get kind of interesting. All right, take a few minutes, see what you can do with that one, and I'll see you in the next video.